Good morning. So today will be the final lecture on our course opto-electronic devices. I think we will be finishing almost all the. We have covered almost all the topics, and we'll try to revise it in the future lectures. Anyway, so today we are continuing with module number 6, and we are going to look at basically 4 different topics today. And I think you have already studied the first two in optical communication. So first is like different types of add drop multipliers. Then you want to look at the optical interconnects, then wavelength converters and optical bistable devices. So these are the topics that we are going to cover today. So basically you are expected to understand the different types of each of these components and its working. So add drop multipliers, as I said earlier, you have already studied in optical communication. So basically, the wavelength of optical carrier acts as a header which spatially routes itself to go to actual place. Now, when you transmit through a fiber an optical signal, now it might be possible that different data might be needed to reach at different places. Now, you need to have some kind of a mechanism to route all these signals. And instead of having a hardware setup where you need to have a complex algorithm to detect and route the signal, instead, what we can do is like you have a wavelength of the optical carrier. Now that wavelength will act as a header. Header means the header will have all the information on to which receiver that it should go or what should be the target receiver. So if you have some such kind of mechanism, then you don't want that extra hardware to do all this stuff, which will reduce the cost, which will increase the efficiency, which will increase the bit rate, etc., etc. So a specific wavelength can be dropped and then can be processed locally. So in the fiber, you will have different wavelengths which is transmitted. Now, at some point, a receiver might need to extract one such wavelength. It does some processing and it might give it back to the fiber so that it can be transmitted and received at the different receiver. So basically what here we are doing, you are dropping one wavelength here. Then you are processing it locally. Then if it is needed, then you can send it back to the fiber so that it can be processed at some other receiver. Okay. Similarly, the optical multiplexer is termed as adding and retrieving information from a particular slot in the electrical domain. So all these things, all the processing is being carried out in the electrical domain. The transmission is happening in the optical domain, but the final processing happens in the electrical domain. Now, what are the advantages of add-drop multiplexers? So the important one is the flexibility for choosing a large number of channels without significant crosstalk. Okay, so you have this multiplexer and you have basically, you say a demux and a mux as a multiplexer. So you can have large number of channels coming in. You can separate out one, or you can have one channel coming in and you can separate it out multiple. So all this you can, since it's an optical communication framework, you can have any number of channels. Okay, there is low attenuation, large tunability, high stability, low cost. Okay, and there's insensitivity to polarization fluctuations. Now, when this data gets passed through the fiber, now the problem is there is a huge bundle or a chunk of data which is being passed. Now, and each of this data will have a different types of polarization. Now, that polarization can interfere with other, which will cause polarization fluctuations. Now, using this add drop multiplexers, you can identify this fluctuations, or you can reduce the sensitivity of fluctuations when the signal is being passed. Now you classify auto multiplexers into three groups or three different types. The first one is add-off multiplexer with permanent add-off pattern, that you permanently add a wavelength or permanently drop wavelength. Then add-off multiplexer with adjustable add-off pattern for one signal. This means you can take out one particular wavelength and you can add that particular wavelength. So multiple wavelengths might be coming in. You can extract one wavelength and that same wavelength can be added. The other wavelengths cannot be added. Then add-off multiplexer with adjustable add-off pattern for multiple signals. Now in this case, you can extract any number of wavelengths and you can add the same number of wavelengths back to the fiber. This is the third scenario. So we will see each one of them. So this is the permanent add-off pattern. So you see that there's a demultiplexer in which you have one signal or one input coming, which will have multiple lambdas, lambda 1, lambda 2, etc. Now demultiplexer will separate out each of these wavelengths. And you are actually dropping one wavelength to the receiver A. Now this wavelength cannot be added back to the fiber. And instead you can add a different wavelength B to the multiplexer so that all these wavelengths can be bundled and transmitted through the fiber. So here the wavelength which is dropped at A cannot be added back. The wavelength which is added to B cannot be dropped at the same before this multiplexer. This is called as permanent add-off pattern. Now there's an adjustable add-off pattern for one signal. So you see here, this input has large number of wavelengths, lambda 1, lambda 2, up to lambda n. Now there's a tunable filter, which we have seen in the last class, that it can extract out one particular wavelength. Okay. So it excited one particular wavelength. It has dropped one particular wavelength. It has gone to the receiver. The receiver did some processing. Now I want this wavelength to go back to the fiber so that this can be processed at some other receivers. So there's a tunable source which will add it back to the fiber using a coupler. So this have all the wavelengths except lambda p. So lambda 1, lambda 2, up to lambda n without no lambda p. So lambda p will be added back in the coupler and it will be transmitted through this fiber. This is called as adjustable add-drop pattern for one signal. So only one particular wavelength can be added and the same wavelength can be dropped. Okay. In a similar way, you can add drop for multiple signals. So if you look at this picture, you see that there are 4 wavelengths coming in. And you drop one wavelength. Okay. In the next, you have 3 wavelengths, you drop another. 2 wavelengths, you drop one, and the last one. Now each of these wavelengths is dropped here. Also, this wavelength can also be added to the coupler. So this is lambda 1, this is lambda 2, this is lambda 3, and this is lambda 4. So 4 wavelengths has come into the coupler. Now it can be coupled back again, and now the output will be lambda 1 to lambda 4. So although we have dropped all the wavelengths which is coming in, we have managed to couple it back all the wavelengths. And we have managed to drop each of the wavelength for further processing. So this is called as adjustable add drop pattern for multiple signals. So multiple wavelengths can be dropped and added. This is add-on multiplexer. Now coming to optical cross connects. As the name indicates, if you have one input, now this input can be transmitted to this output or it can be transmitted to this output. This is called as a cross connect. Or if the input is at 2, it can be transmitted to 1 or it can be transmitted to 2. So basically you are crossing the input to different outputs. Now you can connect multiple cross connects like this so that you will have multiple combinations possible. So you can have multiple cross connects. so that you finally can make sure that your whatever be the input at whatever be the end, you can have the output at your desired output port. This is called as optical cross connects. So amplifier gate switch works almost similar to that of a cross connect. So you have an input here, so it can go to this output. Similarly, this input can also go to this output. This is basically the amplifier gate switch. So instead of directly having a cross connect, there's a switch kind of here, which will make sure that to which output it should go. Okay, this is amplifier gate switch. Now coming to wavelength converters, we already know about this modulation that we have seen analog communication, digital communication. Like we do some kind of a modulation to the input message signal, which is of low frequency. We modulate it with higher frequency so that it can travel more distance. It can travel more distance without much attenuation. It will have, it can transmit the information without much loss extra. Similarly, you can have something called as a wavelength converters in optical communication. So the function is to convert data on an input wavelength onto a possibly different output wavelength among the set of wavelengths in the system. The same way that we do modulation. In modulation, we convert one frequency to another frequency. In wavelength converters, we convert one wavelength to another wavelength. Now, it might not be possible that we might be able to convert to our desired wavelength. We will be having a set of wavelengths into which we can convert. For example, let's say lambda 1 is my wavelength. I want to convert it to, let's say, lambda n. Now, I might not be having the flexibility to convert to lambda n. Instead, I'll be given set of wavelengths. Let's say I'll be giving lambda a, lambda b, lambda c, and lambda d. So the system has these options available to you so that you can convert lambda 1 to lambda a, lambda b, lambda c, or lambda d. That's called as wavelength conversion. With wavelength converters in the network, a single light path can use different wavelengths along each of the links in its path. So basically, you see, you have a wavelength converter here. You have an input here. Let's say this is lambda 1. Now, this wavelength will this converter will convert lambda 1 to some other wavelength lambda 2. Now, if you choose a different converter here, then lambda 2 can be converted to lambda 3. So as lambda 1 is getting transmitted through the system, it will be converted to different wavelengths possible. Okay, so this conversion is also possible. So the important thing is it can improve the efficiency of the network by resolving the wavelength conflicts of the light paths. Like it might be possible that you have a input fiber which gives lambda 1 as one wavelength. It might be possible that this at this junction there may be some other system or some other source which also will gives lambda 1. Now this will cause conflict in here because both are of same wavelength. It can interfere, it can cause problems. So instead, what we can do is you can convert either one of this lambda 1 to a different wavelength lambda 2 and transmit. Now that will not cause an interference and that will make sure that your data is not lost. Now, the important characteristics of wavelength converters are the transparency to bit rates and signal formats. Transparency means you know what the effective bit rate is and you know that, okay, this is the signal format for this particular wavelength. Fast setup time of output wavelength. So setup time is, you might have studied in your digital circuits. Before doing something or before you start conversion, you should have some amount of time at the input, or the input should be stable before the conversion starts. Now, wavelength converters will make sure that the setup time is very low so that you can immediately do the conversion. So that is called as fast setup time. You can convert both shorter and longer wavelengths. You need only a moderate input power. Possibility for same input and output wavelengths. It is possible that you can have same input and output wavelengths, but finally, the initial input output wavelengths, the original source wavelength might be different. Again, insensitivity to input signal polarization. low chirp output signal with high extinction ratio and large signal to noise ratio. Now, SNR is a very important component in all this communication, because if your SNR is low, it might not be possible for you to detect the data. So because of this, in using large wavelength converters, you can have large signal to noise ratio, which will help you in detecting the signal. And this is a simple. Okay. There are two types of wavelength converters. One is called as optoelectronic wavelength conversion. So in optoelectronic wavelength conversion, you first convert the optical signal into electronic signal. You modulate, then using this electronic signal, you make sure you convert to a different wavelength, and then you pass it to the fiber as an optical signal. And there is all optic wavelength conversion, in which all the conversion is in optical domain. So there is no kind of electronic things which is happening in this part. So that is all optic conversion. So this is optoelectronic wavelength conversion. So you see that there's a wavelength coming in. It's a photo detector. So depending on this wavelength, the photo detector will detect the light. For example, just to give an example, for example, let's say lambda 1 is your wavelength. It might give you an output current of, let's say, 1 milliamps or 1 microamp, something like this, which means that the detector has detected a wavelength of lambda 1. Now this will be given into FIFO. FIFO, as you know, this is first in, first out. So you will have one FIFO in which you might have decided what are the wavelengths by looking at the current. So this is, let's say, lambda 1, lambda 2, lambda 3, etc. Now there's an address decoder which will choose a particular wavelength depending on the entries of the FIFO. Now this FIFO output, the current output, will be given to a tunable laser, and the address decoder, which is basically that the wavelength that you have chosen, will make sure, this combination will make sure that a laser beam of this particular wavelength is produced. So address decoder is just a system in which it will choose what wavelength to produce, and the FIFO output is the one which drives the laser to produce that particular wavelength. So in this example, you produce lambda 2. In all optical wavelength conversion, it is just like we are doing a modulation. So you have this input signal here. Okay. Now there is a continuous wave. You assume this is a carrier signal, lambda 2. This is message signal. Now you do modulation on this continuous wave using this input signal, and it will filter out the unwanted components, and it will give you the converted signal. So this is an optical wavelength conversion. It is just like a simple modulation. Now there is another scenario where in which you use a Mach-Zehnder interferometer converter. So here you are actually doing a phase modulation. Okay, so there's a 3 dB coupler which will create lambda 2 gone to the both of the inputs. Now there one of the input, or let's say this one, will create a phase modulation to lambda 2, and that will be coupled and will be sent as the output. Okay, this is the output, and this is lambda 2. This is sorry, this is the original output, the original input, and this is our output. This is an all optic wavelength conversion using Mach-Zehnder interferometer. The last topic here is optical bistable devices. Okay, so an optical bistable device can be regarded as an optical switch. It has two stable states, on and off. So optical bistable device, you might have studied the like multi-vibrators, etc. So it's kind of an bistable device. So you see, if you look at this graph, this is the input power, this is the output power. You are increasing the input power. As you increase the input power, at some point here, the output power jumps up, which means it has turned on. Now, if you keep on increasing the input power, the output power is high only. Now, let's say I start reducing the output power. Okay, sorry, input power. So I am reducing the input power. So as I reduce the input power, when I reach the position where it has jumped to on state, it will not now jump to off state. Instead, my input power need to be reduced again till at some point for the output power to jump back to the off state. So this is a hysteresis and this is a bistable device. So your on off power, input power, the power at which you have an on and off is not at the same value. So there is some amount of hysteresis for which you have an on and off condition. Okay, the process of going from one state to another state is non-linear. It is because of the fact that when the energy supplied passes a certain threshold, the device suddenly jumps to a state where it remains. Okay, so that's what we have explained. So on and off state doesn't happen at the same input power. So this is called as a bistable device. Now, criteria for evaluating the performance of a bistable optical device is first one is switching time. So how fast you can switch from on state to off state. The amount of time required to switch from one state to the other state to switch back and delay before another switching cycles can start. Okay, so you see that you have a small curve or a slanting line from off state to on state. Now this amount of time it required to switch from off to on is the switching time. Similarly, when you come back, there's a small slanting here, and this is the another switching time that we have seen here. So you see that there's a small slanting here. That is a switching time. Switching energy is energy needed to switch and how much of it is dissipated in the device. Now the problem is when you switch from on to off, there is a small amount of time in which there is a short. Now, due to the short, the electric current or whatever be the parameter, it can flow it at very fast rate, which will cause heat dissipation. So, and the energy during this time is called as switching energy. We should reduce the switching energy as much as possible. The last one is stability. It is stability of two states and specifically the possibility of spontaneous switching. Now, it is possible that once you have switched to on state and you have reached the on state, the output at the on state is not stable. It can just vary. But we should make sure that the on state is stable as it is. Or it might be possible that as you increase the input power again, it might come back and go back, something like this. This should not happen. So if it doesn't happen, it is served as a stable state. So one of the most commonly used bistable device is Fabry-Perot resonator bistable device. So Fabry-Perot resonator we have already seen. You have an incident beam. The beam will, these are two different mirrors, semi-transparent mirrors. The wave will go back and forth between the mirrors. Now there will be a resonance condition which will be present inside this mirror. For all the wavelengths which satisfies the condition 2L is equal to m lambda, where L is the length of the distance between the mirrors. So all this lambda which satisfies this condition will have a constructive interference. So this constructive interference will be seen as a high intensity light, both inside and outside the resonator. So we will make use of this scenario with an extra component to create a bistable device. That extra component is a non-linear optical material. Now this material has a property that the refractive index of this material will change by the intensity of light. Okay. So here in this scenario, there is no such material. So this condition is satisfied because like the path difference between any two waves should be equal to m lambda. If the path difference between any two waves is m lambda, then that waves will create a constructive interference. So when you put a material whose refractive index can be varied by changing the intensity, when the wave passes through this material, the refractive index, as the intensity of the wave increases, as intensity increases, the refractive index will increase, implies refractive index is directly proportional or inversely proportional to the speed of the light. So the speed of the wave will reduce, or the wave will become slower, because as refractive index increases, the density of the material increases, which will obstruct the propagation of wave through that material. The wave will become slower. The wave becomes slower means the wavelength will become larger and the frequency will become smaller. Now, because of this change in wavelength, now if 2L is equal to m lambda, let's say for lambda 1, it is causing this resonation or resonance. Now this lambda 1 will be changed to some other lambda 2. Okay. So by changing the intensity of the wave, you can change the resonant frequency. You can change the wavelength at which resonance occurs. And so by changing the intensity, you can have higher resonance or lower resonance. So this is basically a Fabry-Perot resonator bistable device. There is a hybrid Fabry-Perot resonator bistable device in which, instead of using the intensity of the light, we have an electro-optic crystal whose refractive index can be changed by applying a voltage. Now, how the voltage is applied? Now there is a resonance happening. The wave is transmitted outwards. This is fed back using a detector. So detector will detect the amount of wave which is carried out at the transmitter, out of this setup. Detector will produce a corresponding current. This will simulate the amplifier to give a corresponding voltage. So this voltage is proportional to the amount of light which is getting out. So as the voltage increases, you will have the refractive index also increase, and this will reduce the transmitted light. And the last one is self electro-optical effect bistable device, or SEED bistable device. Now here also you have a reverse bias, you have a load resistor, you have a pin diode. Now when the light is not incident, you have a dark current. When the light is incident, the IP, the current will increase. As the current increases, the drop across this load resistor will increase. And you see that this combination of this load resistor and the diode is in parallel with the reverse bias voltage. Now, when the drop across this increases, the drop across the pin diode will decrease, because this is a constant value. So as this drop increases, the drop across this reduces. And you say this is in off state when the current is so high so that the voltage across the pin diode becomes zero. And when the voltage across the pin diode becomes zero, then the current stops. And this is in off state. Now again, it will start flowing because it is now zero. There is no current. The drop will become across the load resistor will become zero. But because of the applied voltage, it will, depending on the input light, the voltage across this will increase and it will come to on state. So this is called as a self electro-optical effect bistable device. Okay, so I think that covers up the portions. Just go through the slides. I'll also upload the notes, and you can go through the notes also. Okay. Okay, fine. So I think we have covered our portions for our course. Now you can decide what you want to do in the next lectures.